Okay, previously we talked about geometric series, so that was all 12.3. But we only talked about series that we said, okay, start at 1 and go to 8, or start at 3 and go to 17, something like that. But now we're going to talk about infinite geometric series. Those are ones that start and don't stop, like the example here. So the first term is going to be 1/2. The second term is 1/4, plus 1/8, plus 1/16, and so on for infinity. And you can see as it goes on and on, the numbers get really, really small, and eventually they won't even matter anymore. They're so small. They're going to be next to nothing. So there's a couple of things we need to take from this. The first thing is, how do we know this is a geometric series? Well, that's just because in a geometric series, the common ratio, the next term divided by the first term, r, is always the same. So 1/4 divided by 1/2. To do that, we do 1/4 times 2 over 1, multiply it by the reciprocal, which equals 1/2, so 2 over 4, or 1/2. Then we'll check 1/8 over 1/4. 1/8 divided by 1/4. Of course, that means to multiply by 4 over 1. That's 4 over 8, or 1/2. So this is a geometric series because the common ratio always stays the same. However, this is an infinite one. It goes on forever. However, even though it goes on forever, it doesn't mean that it keeps getting bigger and bigger. Actually, in this case, it gets smaller and smaller to where these terms don't even matter anymore. So what we're going to do is find out the sums of infinite geometric series, which is possible because if this number keeps getting smaller and smaller, we don't even have to consider what happens like 100, 200 numbers from now because they actually don't matter. Of course, if these numbers get bigger and bigger and the series is growing, then we can't calculate the sum of the geometric series because the sum becomes infinite as well. But like here, if the numbers get smaller and smaller, we can calculate the sum of the series because eventually those smaller numbers, those later numbers, they just don't even matter. So this is relevant because when we consider it, we can find and graph this infinite geometric series to find out what happens as this graph gets larger and larger. So when you plug in the first term, you get 1/2. So we go over to 1, we dot at 1/2. Plug in the second term, it's really 1/2 plus 1/4 because those are the first two terms. So we put a dot here. The third term is 1/2 plus 1/4 plus 1/8, which is about 0.88. Let's put a dot there. Add up the first four terms, we get 0.94. Add up the first 5 terms, we get 0.97. And as we keep going, when we add, like if we were to do the 6th term, we would add 1 over 64, which is really getting really small. And then when we do the 7th term, we're adding 1 over 64 and 1 over 128. So actually, that's not adding much at all, like we said. So what happens to this graph is it approaches the number 1. So it says, describe what happens to the sum as the n increases. We would say it approaches 1. That doesn't mean to say that all of these geometric series will approach 1. This one happens to. But in order to find out what happens as n increases, you're adding up the sums of the first few terms. So like 1/2, 1/2 plus 1/4, 1/2 plus 1/4 plus 1/8. So then you can find out what happens to the graph as the numbers get larger. Or as the number of terms increases, I should say. We have a formula for calculating the sum of an infinite geometric series. So I just went over like the reason behind it, but there's actually a formula you can use to calculate an infinite geometric series. As long as you know the first term a1 and you know the common ratio r, then you can use this formula. The sum equals a1 divided by 1 minus r, provided the absolute value of the common difference is less than 1. Remember, if the common difference is larger than 1, that means the infinite geometric series is growing larger, and we can't calculate the sum because it just keeps getting bigger and bigger. So the common difference, or I'm sorry, the ratio has to be less than 1. If it's larger than 1, we can't calculate it. It has no sum. It's just infinity. So here are two examples. Find the sum of the infinite geometric series. And as you remember from 12.3, this is the formula for a geometric series. So looking at this, we're able to get the information from this chart. So it says find the sum. We have S equals A1 divided by 1 minus R. Of course, A1 will be this term in front, that's 5, divided by 1 minus R. So, or divided by 1 minus R, yeah. So 1 minus R, which is 0.8, because it's in this formula, A1 times R. And this equals 25. 5 divided by 0.2 is 25. For the second example, it doesn't give you the formula, but you're able to tell what A1 and R are yourself. You just might have to calculate them. So we know that A1 is the first term. A sub 1 is this first term. So A sub 1 is just 1. So S equals 1 over 1 minus R. We need to figure out what R is. That's the common difference, the ratio that changes between each one. So to find that, we're going to do negative 3/4 divided by 1, which is negative 3/4. So we're able to plug that in for R. 1 over 1 minus negative 3/4, so plus 3/4, equals 1 over 1 is 4 over 4, so 1 over 7/4. To divide that, you multiply by the reciprocal, 1 times 4 over 7, and you get 4/7.